Greetings, ma'am. We are delighted to have the opportunity to present our project to you today. We have put a great deal of time and effort into this project, and we are excited to have the chance to share it with you. We hope that it will give you a good sense of the work that we have done and the progress that we have made. These are the contents that we are going to be discussing now. This will be the flow of our presentation. So, introduction to cloudlet architecture. Cloudlets are a type of edge computing architecture that aim to bring the capabilities of cloud closer to the users. In cloudless based system, small low power servers are placed at strategic locations such as the edge of a wireless network to provide users with access to cloud services with lower latency and higher performance than would be possible with a remote and centralized cloud. The cloudlet architecture allows for the offloading of compute intensive tasks from mobile devices to the cloudlet, reducing the strain on the devices and improving the user experience. It also enables new applications that require real time processing and low latency interactions, such as augmented reality and virtual reality. Cloudlet architecture is better than client server architecture in several ways. Firstly, as mentioned before, it brings the capabilities of the cloud closer to the user, reducing the latency and improving the performance of services, as we can see in the diagram. Secondly, cloudlets can offload compute intensive tasks from mobile devices to the cloudlet, reducing the strain on the devices and extending their battery life and performance. This can improve the user experience and enable the use of more powerful applications on mobile devices, as will be discussed in further slides. And cloudlets can also provide a more efficient use of network resources by allowing for the caching of data and the execution of tasks locally, reducing the amount of data that needs to be transmitted over the network. As we can see, if the networking data is completely federated to the cloudlet that is shown in the diagram, we can significantly reduce the amount of network resources that are required to push the data through the entire network. This can reduce the network congestion and improve the reliability of our system. In today's world, people are constantly on the move and rely on the smartphones and tablets to stay connected and access information. Mobile cloud computing allows the users to store, access, and share data applications over the internet rather than on their device's local storage. This technology enables the users to access their data and applications from anywhere, at any time, and on any device. It also allows for seamless collaboration and sharing of information. The mobile cloud computing architecture consists of two major components, that is the virtualized computing core and the user application. The virtualized computing core is a hosted cloud service that hosts multiple cloud computing services that are required to run on the mobile device. And the user application is uh, a normal application that has been fine-tuned and optimized to leverage the mobile cloud computing architecture. This diagram shows a broad view of the mobile cloud computing architecture. As uh, as you can see, this allows the users to access data and applications from the cloud instead of storing them locally on the device. Uh, so when combined with mobile cloud computing, cloudlet architecture can provide mobile devices with access to data and applications that are stored and processed in the cloud, while also leveraging the benefits of cloudlet architecture. For example, a cloudlet could be used to provide mobile devices with access to data and applications that are stored in the cloud, while also providing local processing and storage capabilities to improve the performance of the services. This can provide users with a seamless and efficient experience regardless of their location or network conditions. Some of the applications of cloudlets in mobile cloud computing are crowdsourced video processing. Uh, that is, crowdsourced video processing requires an extensive collection of videos from many video captured mobile devices. This can be used by law enforcement. Facial recognition. This essentially detects human faces and recognizes them by finding a match for these faces in a database in real time. This entire process is very computationally expensive. Then virtual reality. This involves realizing a real world view of a real or fictional place with additional information such as spatial awareness, gyroscopic awareness, sound on top of the visual data, and much more computation. And it's also much more computationally intensive. Uh, and healthcare. Finally, accessing patient records through mobile device is fairly straightforward with cloud computing. But mobile healthcare also allows for huge volumes of real-time data to be stored in the cloud and accessed via mobile devices. This makes it easier to retrieve patient records whenever they are needed. Now we are going to come to literature review. Uh, Kanishk.
Okay, thank you, Shashank. The paper titled Cloudlet-based mobile cloud computing for healthcare applications proposed a cloudlet-based MCC model uh, for healthcare applications. Since we already know that cloudlets are small scale, low latency cloud computing environments that are deployed close to the devices that are requesting the central server, this allows for low latency and high bandwidth communication between the device and the cloudlet, thus reducing delays that may occur due to computational, storage, or battery constraints on the device. Use of cloudlets could provide high degree of data integration, which is very much important in healthcare facilities. The authors use a simulation tool known as MCC Sim to compare the performance of a cloudlet-based MCC model to a non-cloudlet-based MCC model. And the simulation consisted of 2,000 mobile users, which was spread in an 800 by 600 meter area, and they were moving in different regions with different velocities and sending packets to the cloud at a specific frequency of zero point 0.1 hertz. The data that was gathered by the simulation tool is presented in this figure. As we can see that with increasing number of cloudlets that are placed, the average delay time is continuously decreasing. Next, in the paper titled A Mobile Cloud Computing Model Using the Cloudless Scheme for Big Data, the authors in this paper proposed a cloudlet-based MCC model, which consisted of a central cloud server, a broker for managing the communication between the clouds and the central cloud, and there were the resource-rich cloudlets that were present. The authors again used the MCC Sim simulator and adjusted the parameters of the model to test its performance by uploading files of different sizes to the central cloud server. Although the simulated tool used was same as in the previous paper we discussed, but the study that they carried out was a little less sophisticated, and the result shows that the cloudlet-based MCC model performs better in terms of power dissipation and time delays with respect to different file sizes that were sent. The figure corresponding to this simulation is shown in the slide. Next.
So coming to the paper that is titled Cloudlet Placement and Minimum Delay Routing in Cloudlet Computing. Cloudlet placement and MDR in cloudlet computing are important considerations in the design and operation of cloud infrastructure. Cloudlet placement refers to the process of determining the optimal location for deploying cloudlets within a network based on the factors such as proximity to mobile devices, network connectivity, and resource availability. Proper cloudlet placement can help minimize latency and maximize the performance of cloudlet-based applications and services. This paper discussed two algorithms which essentially aim to minimize the latency and the number of hops while maximizing I mean the throughput. Minimum delay routing refers to the process of routing data between cloudlets and mobile devices in a way that minimizes the overall transmission delay. This can involve selecting the optimal path between the source and destination based on various metrics. As mentioned before, they are the number of hops, available bandwidth, and the latency. Effective cloudlet placement and MDR are crucial for ensuring smooth operation of a cloudlet infrastructure as they can help maximize the benefits of cloud computing for mobile devices. They're of particular interest to experts in the field as they can help improve the efficiency and performance of cloud-based systems, especially in the context of mobile cloud computing. Ganesh?
In the paper titled The W5 Framework for Computational Offloading in IoT Devices, this paper proposed a method which was basically their own framework, that is the W5 framework, which considers 5 questions: how to offload, what to offload, where to offload, who is responsible for offloading, and the when and why to offload. The framework discusses various offloading techniques such as application migration, record replay, and remote procedure calls, and the specific advantages and disadvantages of each technique. It also considers the benefits and drawbacks of offloading to the central cloud or the edge computing platforms. The authors performed experiments using a resource intensive image application on 2 mobile devices, one that acted as a client and the other acted as a server. This experiment was basically used to answer the when and why questions and compare the performance of different offloading techniques. Now, since the 3 techniques were mentioned by the authors, what they actually mean is going to be discussed in brief. In application migration, the client agent sends the application state, including its package file and any irrelevant images, to the server. For record and replay, the image files already reside on the server, and the client agent is responsible for logging the user's interaction with the application, such as button clicks, and menu item selections. And then these recorded events are then sent to the server to replay all these tasks on a previous application state that is already present on the server. And the final result is sent back to the client. In remote procedure calls, the client agent sends an image and an associated requested task to the server. The server agent receives this image, executes the task requested, and then sends it back to the client agent. Next. Again, this is a brief overview of the questions and what they aim to solve. Uh, the, since the experiment performed by the authors gathered a huge amount of data, the authors presented 5 to 6 figures in their paper. We are only confining ourselves to 2 of those, and we'll discuss what they mean. The experiment consisted of answering the when and why questions, and the 2 figures that are present here show the CPU usage during the remote procedure call and the memory for the associated task. These results, these results show that the RPC performs better in terms of energy consumption and execution time, while the application migration and record replay techniques that the author also experimented on had lower performance, but the author suggested that they may also be suitable for certain types of application. Next. In the paper titled Cloudlets at the Leading Edge of Mobile Cloud Convergence, the paper discussed the use of wearable devices such as Google Glass for cognition assistance and the challenges associated in designing such assistive technology that can help with tasks such as perception and cognition. One challenge that the authors said that was present in this task was the low response time, as delays exceeding tens of milliseconds can affect the user's perception. To address this, the paper proposed using cloudlets for offloading computation, which can save on response time and battery life while also providing low latency and high bandwidth communication. The authors developed an open source platform that they named Gabriel, which runs on cloudlets and uses virtual machines uh, to encapsulate various cognition engines that were interconnected together for wearable devices. A simple example of how cognition assistance will look like when solving a task is given in the figure below. In this task, what we have is a state representation of the associated task, where we go from the left-hand side to the right-hand side. And this uh, task requires us to assemble some stacks. Next. The figure given below basically tells us how the cognition assistance will take place. And there will be two types of guidances, one verbal and one visual. As you can see, for resolving stacks on top of each other, the first step will tell the user to find a green piece and put it on the board. And similarly, other tasks will be carried out. Next.
So the paper titled "The Case for VM-based Cloudlets in Mobile Computing." Uh, in this, the authors mentioned that the mobile devices are often limited in their computing power, storage, and battery life, which can be addressed through the use of cloud computing to offload resource-intensive tasks to more powerful remote servers. However, this approach is hindered by latencies in the inherent WANs, which can negatively impact the user experience and limit the types of applications that can be supported. One solution to this is the use of technologies such as edge computing, which can bring the computing resources closer to the user, or the development of more efficient algorithms and protocols as discussed in previous papers. A VM-based cloudlet is a small cloud computing system that can be run on a single physical machine, such as a server or a cluster of servers, and is used to provide local low latency access to cloud-based services for users in close proximity to the cloudlet. The main benefits of using a VM-based cloudlet include reduced latency for real-time applications like VR and AR, remote collaboration, and gaming. This also uh, improves fault tolerance and resilience for cloud-based services and lowers the cost for users located in remote areas. Kanish?
In the paper titled Enhancing Offloading Systems with Smart Decisions, Adaptive Monitoring, and Mobile Support, the author discusses a framework for optimizing the performance of mobile devices by offloading computation to remote servers such as cloudlets or public clouds. The proposed model also takes into account the time required for data transfer between the devices and the server and compares the performance of running the application locally versus on a remote execution environment. The figure given below basically answers when we are required to offload to the remote server. As you can see in the given figure, there are two paths. In one of the paths, the task is executed locally on the mobile device, and in the other path, the task is executed on the remote server. When you follow these paths, and if you wish to realize performance gain, you will come across equation that is given below. Only when this equation is realized will you be getting performance gains by executing the task on the remote server. Next. This figure deals with the question of answering where the offloading should take place, whether it should be on the cloudlet or the public cloud. Again, there are two paths which deals with the execution on cloudlet and through the public cloud. Again, following these paths, if you again wish to realize performance gains, you will come across an equation that is given below. Only when this equation is followed are you going to realize those gains. Next.
The limitations.
Ah,
Cloudlets have several advantages in mobile cloud computing, including improved performance, enhanced security, increased reliability, reduced costs, and improved privacy. However, they also face challenges related to scalability and interoperability in development. Mobile users can only access cloudlets within a certain range, and the scalability of cloudlets is limited by the number of cloudlets in the area, the financial conditions of the providers, and the capacity of the Wi-Fi connection. There are also challenges related to interoperability with other technologies, security and privacy issues, resource allocation and energy efficiency issues. These challenges can limit the potential benefits of cloudlets and make it difficult to integrate it into existing monolithic cloud systems. Future work. The convergence of mobile cloud computing and cloudlet technology have the potential to significantly improve the delivery of cloud-based services. Some areas of focus for further development in this field include improved scalability by combining the benefits of both technologies, designing new services specifically for these paradigms, enhancing security and privacy through the use of a local nature of cloudlets, and exploring new pricing models that can take advantage of this new paradigm. This convergence has the potential to enable new and innovative ways of delivering cloud based services for new users, and it can also provide new opportunities for researchers, developers, and conclusion. A study has found that cloudlets can improve the performance of resource poor devices by reducing network latency and supporting heterogeneity, leading to improved response times for applications. The use of cloudlets can also provide resiliency. Our study also examined the complexity of certain aspects of cloudlet technology, such as discovery, process migration, and remote execution control. Despite these challenges, the integration of cloudlets into smart city development and their usefulness in hostile environments make them a viable option. Smart systems often face challenges such as low latency and reliability, which can be addressed by the use of cloudlets that offer proximity, high bandwidth, and ultra low latency. In our study, we have seen frameworks which help offloading decision making and can help us in realizing actual performance gains under a specific set of conditions. Thank you.